I also want to thank you for having me in Seoul this week. This is my first time to Korea, and you have been a very gracious and hospitable country. So thank you very much for that welcome that you've given me. And today we're going to talk about VxWorks and where we're going with VxWorks. And specifically, when you talk about VxWorks and where it's been and where we're going, I actually want to look back first and see where VxWorks cut its teeth. Back in the 80s, operating systems were just coming of age, and the 32-bit processor really found its mark in the 1980s, and certainly VxWorks was there in this world to start automating and creating some abilities for systems to rely on an operating system to do part of the job. No longer was it fully customized software, but software that you could rely on to build your application. In the 90s, we saw several things. We saw digital devices, more and more things that used to be analog or some other dedicated things. Those were coming of age, getting more and more processors involved. And the internet explosion, companies finally figured out that there was some value to the internet. It wasn't just about hooking up universities, but it was about connecting things to the internet. And VxWorks was there. In the 2000s, we saw the multi-core revolution, where the demand for higher performance processing, coupled with the need for low power, driving these multi-core processors. And every operating system vendor had to look at this and decide if they were a player. And VxWorks was there. So that takes us through the 2000s. But we're in year 2014. In the 2010s, we see the Internet of Things. And as we got an introduction before about what the Internet of Things looks like, it's many things, and each company is going to be unique as they approach the Internet of Things. And we see the ability to expand your application. So it's no longer just about the end device. It can be about the cloud devices and the devices that are data aggregators. Now there's several reasons for this, but if you look at this chart, you can see that there's tremendous growth in what's going on in terms of the number of devices that are connected to the internet. In fact, it's exceeding the number of people that are connecting to the internet. Things are outnumbering people. And the markets, as you can see, they're diverse. And they've been growing. Each one of them has been growing its market share. So there's some tremendous value in embracing the Internet of Things. If you look at the Internet of Things, and we start with the left-hand side, the edge devices. That's typically where VxWorks has been, and we still are. But on this left-hand side, it's talking about how do we connect these things and make sense of the data so that systems upstream, all the way to the cloud, could take advantage of it, all the way along. And it's from those edge where you're talking about the different applications that are very dedicated, doing processing. Maybe more processing out here at the edge, maybe less. Maybe being able to scale between the two as necessary. Now, VxWorks has always had safety and security as key tenets of VxWorks as a real-time operating system. And scalability is also there, but we've taken it up a notch. We've increased our ability to scale VxWorks, and I'll show you how that works in a minute. We also saw with the Internet of Things, it's very important to look at the connectivity, because it's all about connectivity. If you can't connect to the sensor and make sense of that data, then we've missed the mark. So how do we enable connectivity? Graphics. A lot of these edge devices that used to have no interface at all, now companies expect to see an interface. And what does that interface look like? So we've enabled some features for graphics in VxWorks. And finally, virtualization, to be able to take systems and maybe take 2 or 3 different subsystems and combine them into one using virtualization as a technique. So for VxWorks7, we're going to look at these 3 key tenet areas: safety, security, and scalability. Scalability. Now there's 2 axes to scale. The first is on the device itself. We want our customers to be able to run on really, really small hardware, and we've got some components that will allow you to run on these new 32-bit microcontrollers that are limited in the amount of RAM available to run an application. So you can run in a really tiny space with our microkernel, all the way up to companies that are trying to do as much processing on the edge as possible in a compute-intensive fashion, and looking at ways of taking advantage of other pieces of hardware that are there so that they can increase that, be it a DSP or an FPGA or graphics in a general purpose GPU framework. But all this is at the edge, doing that processing from very simple to very complex and anywhere in between. But there's this other axis here, scaling across to the cloud. So it's easy to think of these edge devices as connecting to the internet. But a lot of times, if you have something going on that you have some sensors, they're going to be hooked up to some data aggregators right there on the premises. And maybe some decision making could be made there. And you can use VxWorks APIs on the edge. You can use VxWorks APIs up here in the data aggregator. You can even use them up here in what I'll call the fog. So it's a cloud, but it's closer to the edge than the cloud. So maybe this one is servicing a full factory. And then in the cloud, being able to scale across however many factories there are. If there's 100 or 200 or 1,000 factories across the world, what can we learn in one factory that could apply to the other factories? So being able to take the data, make decisions at the edge or as an aggregator in the fog or in the cloud, and being able to scale all the way across. So that's something that VxWorks can do for you. We do have some applications that are running up here in the cloud that are running VxWorks, and it allows you to use the same set of APIs all the way across. So it matters in terms of what you need to do for your Internet of Things. In VxWorks6, this is how we delivered software. We took the integrated development environment, Workbench, and we locked down a particular version of that. We tested it with a compiler or a set of compilers, and we locked down the version of that. Again, with the build tools that were there, we locked down that. The middleware and the apps that were there, the kernel, the architecture support, the drivers, and the BSP, they were all locked down to say that this whole thing is tested together, along with creating a DVD and all the necessary pieces that go into making a product. And this whole thing would lock down 4 times a year as a release. If you're a VxWorks7 customer or a VxWorks6 customer, you're familiar with this. We pretty much do a quarterly release. And it's continuing today, where we'll still release, and we're testing this whole thing together as a single entity. You know it works, it's been well tested. But there's some issues with it. What if we can take this environment and break it down a little bit and make it more scalable? So we set out to do that, and that's what we're going to show you today. So we transitioned from this large footprint where everything is tested and locked down, and this is the release and the revision that you have, and broke down VxWorks into its core components. So there's a VxWorks core component that is versioned and revisioned, but its APIs don't change. The CAN bus or the file system or any of these are just examples. The entire operating system went through, and we refactored the code to make it to make it dependent on the things it needed to depend on, with hardened APIs on the top of the package that are fixed, and the APIs in the core packages are fixed. And therefore, for the next 3 years, we're not changing these APIs. We can change the internal components. We will not change the interfaces. What that means is our ecosystem partners can standardize on VxWorks7, And they know that they've got a revenue stream. And just because at 3 years, once we turn this off, there's still another 3 years of support. So you're going to get at least 6 years of shelf life for VxWorks7 without having to change to upgrade or migrate forward. There's another area. So let's take an example first. If you were about to release a product, you're about a month from release, and you discover there's a problem in your product. And you suspect maybe it's in VxWorks, and you're starting to look at the file system itself. Let's say we're on the VxWorks6 paradigm. What's the last thing that you want to do if you call Wind River and we say, we think it's fixed in the latest release? We've been testing for 6 or 8 months in your own factory, and what you're doing, you've been testing it. It's been soaking in your environment. Do you want to take a new version of the operating system to fix this one defect? It's a hard choice. Now maybe we can do some things for you. But let's look at the VxWorks7 paradigm. Because over time we'll release version 1, then a version later on version 1.1, and maybe even later on it's version 2. Remember, the APIs are fixed on the bottom and they're fixed on the top. So we have clear dependency trees on what packages depend on what APIs. So when it installs, we know which one is there. So at configuration time, and let me step back a bit, we can actually install, and this is something that I haven't seen anywhere else in the marketplace. We can install all 3 versions, or however many are there. Let's look at that same situation. You are a month from release, and you discover that there's something wrong, and you suspect it's in the file system. So you go to the servers where our code is resident, and you start looking at, oh, there's a few other versions of this package available. So you can install version 1, went backwards. You can install version 1.1 and version 2 at the same time. They are all installed in your system. And at configuration time, you can choose, well, 1.0 you've been trying. Let's try 1.1. It's just a configuration parameter change and build. Test it out. Solves your problem. Doesn't solve your problem. Let's go to 2.0. Try it again. Let's say that, well, if it solves your problem, it's just that one package that changed. Everything else in your environment is exactly the same. Only one component changed. Now, how willing are you to take this one component that solves a problem and yet it leaves the rest of your system intact? So this is a tremendous value for our customers. And in addition, let's say it didn't solve it, but in talking to support, they figure out what the problem is. We can rev the package to 2.1, release it, because we're not releasing quarterly. You don't have to wait 3 months. We can actually get these done within a month if necessary. We can get a new package out there that you would then have access to. You could download it and try it out. So it helps when you're looking at a defect in the system to be able to fix that defect and get it out to you. So we see this as a tremendous value for VxWorks and for our customers moving forward. Now the microkernel. If you're familiar with VxWorks, it's represented by this big kernel, and you have this little guy next to it, the microkernel. Now, you can run this thing down to about 2K worth of memory. That's pretty small. It doesn't do a lot at 2K. But if you provision the system with several tasks, several operating system constructs that it needs, then maybe you're running at 20K. So if you can run a full system in 20K, these new microcontrollers that have come on the market can consume VxWorks, the microkernel, and you can use it in your environment. So having a very small thing. The other thing that we get is 25 microsecond boot time. So that far surpasses what you can do with Linux, and it certainly surpasses what you do with the standard VxWorks kernel. So if you need these kind of times, you need these kind of space restraints or constraints on your system, you certainly can take advantage of the microkernel. And the thing is, it's hard real time. So you haven't lost your real-time deterministic behavior. It's multi-threaded, so you can actually run it in an environment where there's multiple threads running, multi-core, so it can run on distributed cores in your system, and it's power management ready. So you're able to scale depending on your application's needs and power up cores and power them down as necessary running the system. And where we see it fitting, remember that edge. So on the high-end edge devices, you're probably not going to run that piece. But if you've got a very small, say a sensor, and that sensor's got to collect data on the factory floor and then present that data up to the cloud somewhere, you could run the microkernel out there, have a communication channel, and then run a standard VxWorks somewhere else in the factory. And now you've been able to distribute your application across, taking advantage of the microkernel where it makes sense, and VxWorks where it makes sense. So it gives you a lot of flexibility in where you choose to put what operating system or what kernel fits your needs best. The other is these new big little architectures where you have multiple big cores available. You could certainly run the standard VxWorks kernel on them and take advantage of its set of features. But you might have a lot of these little cores that are available. Well, you could run the microkernel on there. And so now you could take something that may have been distributed on 3 or 4 different subsystems, combine it into one SoC, and then farm out the application to the different microkernels and as well as the kernel itself. Now you've been able to scale your application and compress it onto a single system. So why should I care? So at the end of the day, we want to make systems better, faster, something. And the value is that because you have the ability to scale, you can use a single software platform for both small and large footprint devices. So if you've got those really tiny ones, all the way up to the very compute-intensive applications, we're there for you. If it needs lots of communication channels, or if it needs graphics capabilities, it can do that. And the impact is, since you can use it, you're standardizing it. That means your engineers know the same APIs. They're able to use those APIs across all those areas. And the cost of the BSP. Now the BSP is going to be common that you're able to take advantage of that. The ability to certify the pieces that you need. So there's a lot of stuff just in terms of being able to scale that certainly enable you to essentially save money in your projects. The other one, and this one I touched on, was the patches only when you're needed. Remember that question that was really hard to make when it was the whole operating system, became really easy to make when it's just a single component. And if we can find ways to enable that through the scalability or the modularization of the system, that will enable you to be able to make that decision much more quickly and much more efficiently and solve the problems and get your product to market with less defects. And finally, looking at the marketplace. Today we know what protocols we support. But tomorrow, there's going to be a brand new protocol. And we don't know what that is today, but you're going to discover it, and we're going to discover it, and we're going to say, how fast is it going to be till we can get that protocol implemented in VxWorks? And because of the way we've designed the system, we don't have to re-release everything. We can just add additional packages that enhance the system with that new protocol that's come out. So this will allow us to scale our engineering resources as well. If it's extremely important, we can put a lot of resources on it. If it's not as important as other things, then we can put fewer resources on it. But we can scale internally as well to focus our attention on what matters to our customers most and get those protocols out the door more quickly. So let's turn our attention to safety. Now VxWorks, if you're familiar with VxWorks, has been used in all these different markets down here. And we're keeping that legacy alive. So certainly from the medical, from the multi-core environment, the airborne environment, railway, and avionics, all these standards down here we're addressing with VxWorks. And some of them are happening now, some of them will happen shortly in the future. But having these profiles available so that you know you're able to take an application that needs to be certified. You can depend on VxWorks7 to be that vehicle where we can take it and we can do DO178C if it's necessary on that system and provide that, that capability there. So we see this as a, in the past, if you may have used different versions of VxWorks in order to achieve certain goals, we're looking to do that with VxWorks7 so that you could standardize on one operating system in your environment to be able to provide the functionality and the certification ability of your system. Now, one of the other things is the ability to wall off the system. Now, we've had this with our hypervisor. You could certainly create instances of the operating system that would exist in walls. But what's different about this is to actually take VxWorks and run it as VxWorks, but take a real-time process and wall it off. And we've changed the scheduler so that we now provide both time and space and resource partitioning of the system. Now, what does that mean? In this case, you have an SIL3 level. So this is safety. It may have been certified in your environment, and it cannot crash. If it crashes, maybe somebody is injured. So it's very critical that this real-time process runs, and it runs when it needs to run. It gets access to the machine. So we guarantee time and space and resources that it needs to get access to. So this one, maybe it could crash. And that's okay. If it crashed, it doesn't bring down this system over here. So the system would tolerate that. If for some reason this one crashed, you could reboot this one, bring it back up, and the system never lost a beat over here while this one was. If it ran amok and started trying to take over the machine, this one would still get its guaranteed amount of time and space and resources. So we say that is very important for the safety of systems, to be able to produce systems that will do that. And one of the benefits is if you can certify this piece here, then you can change this piece over here without having to recertify this piece. So it's also a value when you try and look at software that needs to be certified and software that doesn't need to be certified coexisting on the same platform. So why should you care? Well, as I just said, run safe and non-safe applications on the same device. And this gives you the ability to use that same piece of hardware using two separate real-time processes and be able to keep it together. So you've now been able to maybe aggregate things that were separated in different subsystems, put them in the same system, and yet allow them to share the machine in a way that you guarantee the pieces that need time with the scheduler get that time with the scheduler. And the ability to update those non-safe applications. So again, this is one where being able to upgrade that piece without having to change it reduces the cost of being able to certify the piece that absolutely needs to be certified. So you could use this as a way of segregating your application into the domains that need to be certified and the domains that don't. And you can change the ones that don't much more frequently. All right, security. Let's look at security. Now, today there are more threats going on to devices on the internet than there ever have been before. And we don't see this trend decreasing, we see this trend increasing. The question is how fast, when you see that there's a threat in the environment, something is going on, somebody's taking advantage of some loophole, how fast can we iterate around and close that loophole? Now, we participate right now in those reports. As soon as we're aware of something, we're looking at our implementations, making sure that these threats are minimized on VxWorks. The question is, how fast can we iterate through to make sure that the system is closed and you can go to maybe a next iteration very quickly if it addresses a security need. These come from several areas. Certainly the environment where the development environment, where the software is, where that's installed, to the access points, how do you gain access into the system? Since it is the Internet of Things, the internet is coming in here. Well, what's open? What's available to a hacker or somebody that does not have your best interests in mind, and they're trying to take advantage of the system. And then storage on the device. We look at those 3 areas. There are 4 pillars. So first of all, in the design, we have ways, since we've installed all these packages on your system, an engineer could actually go in and insert code into the software database. Well, it's very easy to detect if that's happened, and you can actually look at it. Now, you might have patched your code. You have source code, so if you decided to patch VxWorks, you would see it and could detect that it's there and then mark that block saying, I know that that block is there. But if somebody put in code without your knowledge, you would actually discover it. So it helps prevent intrusion at the design time, where it's very difficult to fix out in the field or later on. You need to detect it early. And then from booting the system, making sure that binaries are trusted and that no untrusted binaries run on the system. And at runtime, making sure that the system that's running, and I would say that there are 2 pieces to the runtime component. One is attacks on the machine itself, where somebody's trying to get into a port and take advantage of it. Maybe there's a maintenance port that's been left on. Maybe there's a debug channel that's been left on. So taking advantage of what's available here, but also data on the move. Having the encryption technology to allow you to encrypt the data that's on the move. So if somebody starts looking at that data, can they make sense of it? And if you need them to not be able to see it, you can certainly lock that down. And then finally, at power down, if somebody could go in and look at the flash components on the board, can they make sense of that data? Is it stored in plain sight or not? And I have a story here when I was working on a system, and I needed to know what was going on in the system, and I didn't have the passwords to the system. So I put my own ROM. Remember this boot time thing? I put my own ROM in there. It didn't detect that it was a new ROM. And I ran my code. And my code said, take everything that's in this storage and dump it in a way that I could understand. And the watchdog would reset it. But I would get a little bit of data out. And I'd change the pointer, update the ROM, get a little more data out. And sure enough, as I'm going through it, I see my password. Interesting. My password was stored unencrypted in plain sight. And I went, wait a minute, this must be the area where all the passwords are. So I sort of went through and I found it, and lo and behold, I found the system password. So something that the company had lost, I was able to retrieve. And that was not trying to be malicious. If somebody was malicious, they would have found the system password and had access to everything in the system. So very important to find ways to prevent this, is certainly if you're worried about security. Now, establishing a root of trust. And this happens, so certainly the system itself, as we come up, the very first instructions that are run, are they secure? So if somebody could come in here and replace and put their own bootloader in, well, there's very little that you could do after that, because they could boot whatever they want, and they've already got it. So you need to establish root of trust very early in the boot cycle. And after that, you've got an image. So once you know that your bootloader is secure and it's been validated, and if the hardware allows you to, you can validate it in the hardware, or you're trusting the environment. But either way, you could take that image, and if it's a real bootloader, it's going to check the signature on the VxWorks image. Make sure that that image is authorized to run. And you do the same thing up here, where you've got applications that are running, either built into the kernel or the runtime processes, and we can actually look at those signed as well. So you establish root of trust all the way at the bottom, all the way up through the applications, and make sure that what's running on your machine is intended to run on your machine. The other way to look at this is when the data is being accessed, what applications need to get access to the different components? You might have one that's all it's doing is it's a maintenance channel. Well, if it's a maintenance channel, it's coming into the box, but it doesn't need to get access to, say, the radio. It's using an Ethernet connection or a serial connection. It's doing something with that, but it doesn't need access where it's not doing any work. If it needs it, then you go ahead and allow access. So you can limit the access on a per user, which is really a per process environment. Say this process needs to get access to the following resources in the machine, the following sets of APIs. And as long as it has access, it can. So if somebody does manage to get into the maintenance channel, they can't mess with the radio. So very important to keep the two worlds separate, or however many different user constructs you need in the system. So why should you care about security? Well, certainly you want to have a comprehensive security solution that will exist across all the aspects of security, not just one point solution, but have access to all of it. And that is something that's been in VxWorks, and we will continue to invest in this area, and it gives you a solid foundation from which to build. The other is, maybe you don't want all that security. Maybe you've got a compute-intensive application that's going to use most of the CPU. You don't want to burden it, and you know it's in a secure, trusted environment. You can turn on and off whatever pieces are necessary. So the security is not forced upon you, but it's there as a resource for you to leverage to make sure the system is as secure as you need it to be without being too secure that you might lose some productivity on the device. I want to go through some cute new features of VxWorks that have been added to VxWorks7. The first is VxWorks7 is graphics ready, out of the box. If you've worked with graphics on VxWorks, we've done some things in the past where you could do it. It was an add-on. At this point, if you are working with some of our market-specific platforms, it's in the box. From day one, you have access to it. If you have a device that needs to have graphics support, you can build user interfaces like these with the software that we provide. Now, what does this look like? Tilcon, if you're familiar with Tilcon, this is a product that we own, and we put it out with VxWorks7 as a standard component. It has a graphics designer tool, so you use this on Windows or on Linux. It will work with the 2D graphics stack that's available. It'll use the OpenVG standard, and this is another component, software OpenVG. So all you need to have in your system is a frame buffer driver and some sort of input devices that are there. And we've done open standards here for a frame buffer driver and for event handlers. And the software OpenVG stack, you've got the Tilcon component that will talk through it, and you're able to do those user interfaces that we talked about. So it's very straightforward. You have the ability to do that. And in addition, the 3D graphics stack. So we've enabled this in a way that you can use OpenGL ES commands, and this is not enabled on every device. These are very complex drivers, and our teams work for many man-months in building these drivers and making them available. So we will not enable all of them, but we will enable the ones that we see are important to our customers. And if there's one that's important to you that we haven't built yet, then we can look at either adding it to the mix or getting professional services to add it so that you have the right driver here. But this one will provide standard OpenGL ES frameworks. And once you have that, you can run, on top of it, you're able to run things like Qt or third-party stacks that will bolt right on top, and we have customers using that configuration today. I went through this a little bit in the last slide, but the Tilcon UI Designer works with the Tilcon UI engine, so this is running on the target, the software OpenVG stack that's there, and then standard input handlers for mouse, keyboard, touchscreen, and then for output for frame buffer. Connectivity. And the Internet of Things is all about connectivity. So we went out and we looked at what protocols we currently have in stock, and we've added a few, we've enhanced a few. Certainly Bluetooth Low Energy, supporting the health device profile. There's some other profiles that we're looking at. So this capability is testing right now. It's not shipping quite yet, but if there's something that you needed and you wanted to try it out, we certainly could look at doing an evaluation there. The CAN protocols. We had our own CAN protocol stack in WinNet CAN. And one of the key tenets of VxWorks moving forward, certainly in VxWorks7, is if there's an open standard that solves the same problem that we're trying to solve with our own proprietary standard, let's look to adopt it. And you saw it on the last slide with OpenVG. Having a software OpenVG, if you're familiar with WinML, that was a graphics library. We pushed that aside, took some of the components and refactored that code, but we replaced the graphics, the vector graphics component with something that's a Chronos standard API. So an open standard. And here in the CAN bus, you see the same thing. We had WinNet CAN, proprietary. We now have Socket CAN. And Socket CAN will give you the capability of using standard APIs. And if you need something on top of that, we have some third-party vendors that are providing some other pieces that can give you a CAN open stack as well. FireWire, we have customers that are still investing and needing FireWire, so that one is coming forward. The Continua health stack for medical applications, that's supported on VxWorks7. USB, there's a lot of components in USB that are available out of the box, and it's extendable the way that we built it. Then down here in terms of networking itself, this is probably the biggest area when you look at the Internet of Things, the infrastructure pieces that need to be there. Well, certainly IPv4 has been there, and we've been supporting it for a long time. IPv6 is a standard component, and being able to run it in a dual mode, so you can have IPv4 and IPv6 configured at the same time, used on the same network interfaces. So it gives you a lot of flexibility there, as well as the IPv6 ready logo certification. So a lot of pieces there that you can depend on. And then wireless network drivers. We're looking to take the set that we have and augment it over time, because we see that networking, certainly wireless networking, is a big component of the Internet of Things. The BSP was another area that we spent a lot of time on. You can look at this box on the left-hand side, VxWorks6 BSP model, and there were pieces of things that were kernel specific, pieces that were architecture specific. Processor code was in here, driver code was in here, the bootloader code was in here, and the configuration data was in here. So there's a lot of pieces, and if you looked at our BSP, you'd say, wow, this is a complex piece of code. But one of the issues is we're running it here, and let's say the processor code, we find a defect, we fix it. But since it's in the BSP, we might have an adjacent BSP that has similar processor code, but it didn't get the fix because it hadn't been refactored like what we did with VxWorks7. Now, the processor library is common code, and it should be. It's specific to the processor, not to the BSP. So anything that's common got pulled out and is put in part of the platform. The processor library, the driver library, the bootloaders itself, and the kernel pieces that are necessary in the BSP, they're all above the line. So what's left in the BSP? You've got a board configuration file, a device tree, and you've got board-specific code, essentially boot-up code that needs to be there. That's it. That's now the BSP. And to show you what that looks like, the VxWorks6 BSP contained 5,200 lines of code, approximately. If we looked at a few BSPs, that's what we measured. The VxWorks7 BSP contains 72 lines of code. Think about that for a minute. 5,200, much of that code should have been common, wasn't. 72 unique lines of code that matter to this BSP. C files, there were 19 to choose from. Oh, I need to change something to optimize something in the way the CPU is running, the processor library. But it was, remember, it was in the VxWorks6 BSP. Well, which one of those 19 files should you change? The answer now is none, although there are two files, the device tree and the board-specific code. That's it. So none of those would be involved with that. Maybe if you're setting up some special clock settings or something, you might have some code to do that. And that's it. So the maintenance on the BSP, and more importantly, your ability to take a VxWorks7 BSP that we provide and use your hardware. So it's the same SoC. There are only 2 files to look at. How much quicker are you going to be able to adapt to your specific BSP? So to me, this is a tremendous value to our customers looking at code maintenance moving forward. Next, I want to go into the tools with Workbench 4. This is the next generation of tools, and we spent a lot of time in the tools as well as we looked at VxWorks7. And I got to say that when you look at tools, it's one of those things like, yeah, okay, this is interesting. A lot of times you use a tool, and you say, well, this is really great, I can visualize something, and the sales guy sells you the tool, and you go, oh, this is great, and then you never use it. It's too complex. There's something in the tool that, unless it hits a certain threshold, maybe we're not going to ever use. This is something that we actually use internally, and I was working with a customer that had some issues, and we were looking, how do we optimize the system? They were looking to optimize as much as possible in the system. We have this system analysis package that's available. Let's use it. And sure enough, we could get down to the interrupt routines, and we could see, comparing 2 different builds, we could see where an interrupt was latent. Why is it latent? It was showing us some of the bottlenecks in the system. So it's a tremendous value being able to put the system together. It gives you instant access to the code and system behavior, which is great. But it does another thing. It allows you to optimize the code and detect problems. Now, if some of you have worked with Linux, one of the most important debug tools in Linux is printf. With VxWorks, we have dynamic printfs. You don't recompile the code. You say, oh, I want a printf on this statement. If you were going the old way, you'd have to edit the file, add the printf, figure out what you want to look at, and then recompile that code, download the system, and you've got it. Now, you can do this dynamically. Test it out. System's still running. I insert a printf. I can insert a function dynamically in the system. I can insert code snippets at any time to make sure that I'm addressing the pieces I want. Is this fix going to fix it? So it's a tremendous advantage for those people who are trying to optimize the compile, edit, debug cycle and shorten it, which shortens your time to market. And lastly, talking about the BSP, when you migrate from 6 to 7, we spent a lot of time saying, how do we make sure that customers can move forward without a lot of pain? The first thing is we said no API or behavior change. So if you're running an application, you can depend on those APIs. Largely, they're the same. There are a few instances where they've changed. We've documented those changes, so you can see them. And there are migration guides available. The one piece I want to draw your attention to is the BSP. There's a lot of changes in the BSP. So how do I take advantage of that? One of the things we did is we allow you to use a VxWorks6 BSP unchanged, largely unchanged, in VxWorks7. You take the BSP, and if it's one developed by us, or even your own, you probably could do this with little or no modification. You take that BSP, you can drop it in the directory, a certain directory, and lo and behold, VxWorks7 will see it in the configuration. I can build against it. I can actually test and deploy with that configuration. Haven't taken advantage of some of the other things that are available in the BSP, but it's a tremendous ability for you to take VxWorks7 day one, put it on your desk, take the VxWorks6 BSP you have, and start running VxWorks7 on that 6 BSP, day one. Okay, the value pyramid. So certainly, we talked about the modularity and scalability, and that's a key component here. That safety and security is important, and we need to make sure that that's a tenet of VxWorks. We know our customers need that. We've added some components, but certainly graphics, storage, and the different connectivity options. Those are all aspects there. The analysis tools that we talked about to help you in your compile, edit, debug, and even the ability to scale your BSP and minimize what's in the BSP as opposed to what should be common. This is the value that VxWorks7 brings to you. And quality, we've done two things here. where it's code. If this code originates in Wind River, it's not third-party code. There is some third-party code. But if it originates in our walls, we have the source code and it's our source code, there are 0 compiler warnings. We went through and made sure that every line of code would generate no warnings. So you can do that. The other thing we did is we went through with the Coverity tool, and we made sure that everything was Coverity level 3. Since you get source code with VxWorks7, you can run these tools yourself, and you can verify, do I get compiler warnings? You shouldn't. If you do, that's something that we missed. We check it, so I don't think you'll see that unless you're running some odd compiler that wasn't there, has something in the system that's not quite right. Same thing with Coverity level 3. You can run it and you can check it for yourself to make sure that we're there. That says that we've raised the bar on the quality of our code. It certainly is more sound, more specific, and is not left up to misinterpretation by a compiler. So that's VxWorks7 in a nutshell. That's our new logo. You'll see that on our literature moving forward. And at this point, I was going to turn it over to questions. I don't know if we have time for that. So no time for that. So I want to thank you for this time that we spent together, and certainly I'll be available in the back or during time at breaks and whatnot. So thank you very much for your time.
네, 발표 감사합니다.